Take a look at any modern manufacturing floor for smart devices or autonomous vehicles. The physical scale required to produce these machines is massive, but it's the sheer number of hardware and software variations inside them that creates a unique kind of chaos. This chart compares two numbers. The tiny sphere on the right is the total atoms in the observable universe. The massive number on the left, 2 to the power of 260, is the possible feature combinations for a single vehicle line. When your product variations outnumber the atoms in the universe, how do you actually engineer, track, and build them without your entire production pipeline collapsing? The truth is, the physical factory floor isn't the bottleneck anymore. It's the digital and software engineering pipelines that are buckling under the weight of infinite variety. For decades, software and systems engineers relied on a method called clone and own. If the marketing team wanted a new product variant, engineers would simply copy the code and design documents from an existing product, rename the file, and manually tweak it. If you are only building 2 or 3 variations, this quick copy method feels fast and efficient. You get a new product out the door with minimal initial friction. But watch what happens as the portfolio grows. If you find a critical safety bug in product number 100, your engineering team now has to manually track down and patch that exact same bug across 100 isolated codebases. This creates a trap where the math works against you. The synchronization complexity scales exponentially, meaning every new product you sell directly accelerates the collapse of your engineering system. To solve this, the International Organization for Standardization published ISO IEC 26580. It details a framework called feature-based product line engineering, which moves organizations away from engineering individual products and toward engineering a single automated factory that builds the products for them. The core of this standard is the Technical Organization Management Layer, or TOM layer. Think of it as the control room. It sits directly between the raw infrastructure tools used by developers and the business strategies dictated by the executives. The TOM layer operates on a principle called methodology independence. It does not force your engineers to abandon their agile workflows or model-based systems engineering. Instead, it acts as a thin, transparent layer of variability management that slips right over the tools you already use. Because engineers don't have to throw away their established workflows, it significantly lowers the resistance that usually derails major procedural changes, allowing a global enterprise to modernize its pipeline while keeping its engineering culture intact. This control room runs on 3 main engines. First is the feature catalog. This acts as the common language for the entire company, cataloging every possible variation in the product line and defining strict mathematical rules for which features can or cannot coexist. Second, the shared asset superset merges every product asset into one master entity with specific variation points. Third, the bill of features portfolio acts as a selection menu. Finally, a configurator automatically filters the superset based on those rules, instantly outputting a single precise product instance. All human engineering effort is now entirely focused on building and maintaining the factory itself. Manual coding at the individual product level is completely eliminated. To keep this automated factory running, the standard enforces a very strict rule. Every single product instance that comes out of that configurator is strictly read-only. If a developer spots a bug during final testing, they cannot hotfix the product. They must trace it back to the domain-level superset, patch the root cause there, and command the factory to regenerate the product from scratch. Because the products are completely reproducible, organizations stop storing thousands of massive individual product files. Instead, they use temporal baselines, tiny snapshots of metadata that record the exact factory settings at a given point in time, allowing them to perfectly recreate any past product on demand. By locking down configuration, traceability, and change management behind these strict rules, the massive compounding complexity of clone and own is reduced to a clean, flat line. This centralized control completely rewrites the economics of quality assurance. In mission-critical industries like aerospace, testing is incredibly expensive. Now, organizations run those independent unit tests exactly once on the shared superset, rather than repeating them redundantly across dozens of finished aircraft. Companies that endure the initial effort of setting up this factory model reach a financial inflection point, known in the industry as superlinear cost avoidance. This chart shows how that plays out. Under traditional methods, efficiency gains are linear. But in a feature-based factory, as you add more products and more lifecycle phases to the portfolio, the cost to maintain them drops exponentially. The TOM layer, defined in ISO IEC 26580, provides the exact specifications to make this happen. It is a blueprint that lets organizations take infinite crushing complexity and convert it into a highly lucrative market advantage.